For our final circuit example, we have one that is kind of the exemption to one of the rules that I told you earlier in one of the first videos. And it has to do with this middle branch that has two resistors that are actually wired in series within a parallel section made up of three branches. So generally the rule is to always resolve your parallel sections first, the only exemption being if within those parallel branches you have resistors in series, we want to kind of combine those first, and we want to deal with the total resistance of each branch. So anyway, we're going to make a VIRP table as we always do. And the first step is going to be to enter in everything that is known. So we have 5 resistors in this case. We know their resistance is, and we know that the total voltage applied to the circuit is 35 volts. Now, before we actually do anything with these parallel sections, we do want to combine these two resistors first because we want to know what the total resistance of the entire branch is, not just the individual resistors. Since these are wired in series, one right after the other, we can combine them by simply adding them together. So what we're really dealing with is 3 branches with resistances of 3 ohms, 8 ohms, and 10 ohms. That's essentially what we're looking at here. So once I know that we're looking with resistances of 3, 8, and 10, I can combine those according to the parallel equation by taking the inverses of each of them and then taking the inverse of that result. Doing so yields me 1.79 ohms. That is the total resistance of the parallel section. Well, the parallel section in its entirety is in series with the 9 ohm resistor, so I'm then going to add the 9 ohm resistor with the 1.79 ohms, which is the resistance of the total parallel section, to arrive at my total resistance for the whole circuit, which is 10.79, and I can enter that into my VIRP table. Now that I know the total voltage and the total resistance, I can utilize Ohm's law, and utilizing Ohm's law tells me that the total current passing through the circuit is 3.24 amps. As always, I like to draw that coming out of the battery in the top left-hand part of the diagram. We recognize that every electron or all of the current must pass through R1 since there are no other options. So I can list the total current of 3.24 for the current through R1 because all the current must pass through that point. All right, the next step is to recognize that I have my 3.24 amps that is going to flow into this parallel section. You will see that I have drawn the representation of that parallel section in accordance with what I did initially by combining the 6 and the 2. So the total resistance of each of these branches is 3 ohms, 8 ohms, and 10 ohms respectively. And now I can start to apply Kirchhoff's junction rule. The proportions would be 10 over 3 for the first, 10 over 8 for the second, and 10 over 10 for the third, which gives me proportions of 3.33, 1.25, and 1. What that tells me is that the 3 ohm branch will have 3.33 times more current than the 10, and the 8 ohm branch will have 1.25 times more current than the 10. I'll apply my x's, which represent the unknown amounts of current, and I know that when I sum those 3 currents together, they have to enter equal the total amount of current that enters that branch. So I apply my algebra, 5.58x equals 3.24, so x must be 0.58 amps. Well, now I can go back and I can say that in the case of the 10 ohm, it's going to be 0.58 because that's simply 1 times x. In the 8 ohm case, that's going to be 1.25 times x, so 1.25 times 0.58. And in the third case, it's going to be 3.33 times 0.58, and I get 1.93. So I now know how much current goes through each of these branches, 1.93 for the 3 ohm resistor, 0.725 for the 6 and the 2, because that entire branch, what we call the 8 ohm branch, gets 0.725, so any resistors in that branch will get that amount, and 0.58 for the 10 ohm resistor. At this point, I have all of my currents and all of my resistances, so I can use Ohm's law and multiply I times R, and that will get me all of my voltages. And now that I have V, I, and R, I can take any combination of the power equation I'd like, either P equals IV, P equals I squared R, or P equals V squared R. Any one of those will yield all of the power outputs in watts for this circuit. Now, as always, we should double check and make sure that any one pathway we quote unquote spend or we drop the total voltage. So if we clean this up, now that we have our table, one option is to pass through resistors 1 and 2. I can bypass the rest. I can just go through 1 and 2. If that's the case, what we want to take a look at is resistor 1 cost me 29.16 volts, and resistor 2 cost me 5.79. If I add those together, it adds up to 35 volts, so we know we've done that correctly. If we reset that and instead we look at the second option, which is going through R1, R3, and R4, well then I'm going to add up R1, which is 29.16. I'm going to add up R3, which is 4.35, and I'm going to add to that R4, which is 1.45, and if I combine all of those, once again, that's going to give me my total of 35. Last but not least, I could also go through this pathway through R1 and R5, and once again, if I add R1 and R5, I'm going to get just about 35 volts. All three of my pathways add up to the total 35, barring any slight rounding errors, which tells me I have a 99% chance probability that I've done this problem correctly.